Today we're going to continue to talk more about hypothesis tests and confidence intervals. So first thing we're going to discuss is statistically significant results. So if you are a researcher and you are studying something and you find out that whatever you ended up concluding was statistically significant, that is a very good and exciting thing. It means that whatever you tested happened not purely by chance. So I'll give more specific, concrete examples in class. And this is going to happen when your p-value is less than what we call our alpha level. And I'm going to draw this is the Greek letter alpha. We call it the alpha level. So we have actually, until now, been using alpha equals 5. Alpha equals 0.05. So anything less than 0.05 that you've gotten for p-value has caused you to reject the null hypothesis. So we actually call this alpha level, which we've been using as 0.05, our significance level. So there's two names for it. I don't care what you call it. To be honest, we usually just write the symbol alpha, so it's fine if you just do that. So the alpha level is the highest p-value at which we reject a null hypothesis. So by default, we usually use 0.05. However, if you are a researcher and you're doing something very important, like a cure for cancer or something that you want to be extremely certain that it works, you would probably use a lower alpha level. So the other ones that we sometimes use are, so we usually use, I'm going to say we often use 0.01, and of course 0.05 as I said, and also 0.1. Those are the ones that you generally will see. There's other ones that you'll see, but these are the three that we use the most. So just to make sure you're good with the alpha level, I'm just going to say, for example, if you are researching something, and if your p-value is equal to 0.023, so you would reject the null hypothesis only if your alpha, you would reject it, for example, if your alpha was 0.05 or if your alpha was 0.10, but you would not reject it if you were doing an alpha level of 0.01. So the alpha level is going to tell you whether or not you're going to reject your null hypothesis. It's just a threshold, basically. And another definition of the alpha is that, so your alpha level is also going to be the probability that you reject a true null hypothesis. So I'll let you think about what the p-value actually means. I think this is an interesting discussion to have in class because I could talk about it for about 30 minutes, and I'm sure you don't want to listen to me talk about it on the video for 30 minutes. But so just note that the alpha level is the probability you reject a true null hypothesis. So this next part is a little confusing when you first do it, but it's very interesting because it's going to make a lot of connections between confidence intervals and hypothesis tests and our alpha levels. So let's say that you are running a confidence interval and you're doing a 90% confidence interval. What that means is that you're taking whatever your mean is and you're trying to find out the values that are in the middle 90% of this. So your mean would be right in the middle there. And so your confidence interval is going to be around that. So what's going to happen is you are not going to be accounting for 5% on each side. So 5% over here, 5% over here. So that is going to mean that you are using an alpha level of 0.10. So a 90% confidence interval has an alpha level of 0.10. You will also find that a 95% confidence interval is going to have an alpha level of 0.05. So overall, in order to find out which alpha level goes along with which confidence level, you are just going to take, I'm going to call it C% confidence. And you're going to do 1 minus whatever that percent is. So, for example, if it's 90%, you do 1 minus 0.9, you get 0.01. So that is going to be our alpha level. Unfortunately, when you're working with one-tailed hypothesis tests, it's a little bit more confusing. So I'm going to go on to that right now. So if you are doing a one-tailed hypothesis test, which, by the way, if you recall, means, for example, if you have your alternative hypothesis is either greater than or if it's less than. So it's going to be slightly different. So then it corresponds to a confidence interval. For example, if you have a 90% confidence interval, if it is only one-sided, that means we would only look below our 90% range or above it. I'm going to just do below for the sake of this example. So you'll find that this space right here would be 5% below. Up here, the place where we are not even looking is 5% above. So what's going to happen is when we're working with 90% confidence, our alpha level is actually going to be 0.05. It's only going to be the 5% that we have shaded in right there. So another thing is that if you have 95% confidence, you are going to have an alpha level of 0.025. So our formula for a one-tailed hypothesis test, if you have a confidence interval of C%, your alpha is going to be 1/2 of 100 minus whatever your percent is. Excuse me, 1/2 of 1 minus whatever your percent is, because we're thinking about it as decimals. So this topic is usually a little bit confusing the first time you see it. Don't worry if it's tricky now. We'll do some practice on it, and we'll discuss it a little bit more in class. So the next stuff is among the most important stuff in this section, and it's called type 1 and type 2 errors. So sometimes when you do research, you're unfortunately not always going to be perfect. It's really hard to be 100% certain for example, oftentimes we test things, we're only 95% confident, so we can't really easily ever be 100% certain. So sometimes people do make mistakes. So a type 1 error is our first type, and it is when you reject a true null hypothesis. So it's rejecting a true null hypothesis. And this is actually also often referred to as a false positive. And once again, with this, we'll do a bunch of examples so you can see it in context. The second thing about this that's important is that if you look back at our definition above for alpha, and you look at our definition for type 1 error, you might realize that alpha is actually going to be the probability of a type 1 error. So our second thing that can go wrong would be if we end up failing to reject a false null hypothesis. And this would be what we call a false negative. So, unfortunately, the probability for this one is not as straightforward. We do have a nice symbol for it, but the symbol is not very easy to calculate. So, the probability of a type 2 error is what we call beta. So this is the Greek letter beta. It's like a Greek B. And unfortunately, these things often happen, especially in real life. If there was any possible way that you could take complete censuses of every single population, then that would be the way to reduce this. But, unfortunately, that's not realistic. So really, the only way to reduce both of these types of errors is to increase your sample size. And I'm actually going to write that down because it's important. So the only way to reduce both errors is to increase your sample size. Unfortunately, it's not always realistic to do that because oftentimes if you're doing an experiment or working on an experimental drug, it's hard to find enough volunteers that are willing to participate. So this is not always the easiest thing to do. So the other thing that's important to know is that unless you increase the sample size, if you want to reduce one type of error, it's going to increase the other type. For example, if you reduce the probability of a type 1 error, then the probability of a type 2 error is going to increase. So that's why sample size is really the only thing that you can change to control that. So one more important word for the day is called power. So the power of a hypothesis test is the probability of correctly rejecting a false null hypothesis. And unlike the errors that we had, it's actually it's a good thing. So our power is going to be equal to, remember from the previous slide, the beta, which was the probability of a type 2 error, error, our power is going to be equal to 1 minus beta. Unfortunately, once again, beta is very hard to find unless you actually have, like the true sample or the true population proportion. So oftentimes it's just a theoretical value. So we're going to end with a problem from the book just to hopefully help your understanding of type 1 and type 2 errors. It's page 501, number 19. You can go ahead, pause, read through it. So for this one, the first thing you're going to do is state their hypotheses. These ones, you can actually write them in words and you can also write them in symbols. I'm going to actually do it in both, even though they just say in words. So first of all, our null hypothesis is that the rate of home ownership is the same. So you can say either P equals 0.69, or you can say the rate of home ownership is the same. And actually, they only asked you for words. The reason for that is because that's all you really need for this. So the rate of home ownership is the same. The alternative hypothesis is that your rate of home ownership has increased. So that's part A. For part B, they ask you, what will a type 1 error be? So if you remember, a type 1 error would be rejecting a true null hypothesis. And the best way to approach these type of problems is think about what it means when you reject a hypothesis and what it means when the null hypothesis is true. So if this null hypothesis is true, that means that the rate of home ownership is the same. If you were to reject the null hypothesis, that would mean that the city would say that they would assume that the rate has increased. So it would be assuming the rate has increased. So you have to think about what each of these things means. So the best way to phrase this would be to put it all together. You can say that the type 1 error would be that the city council believes that the rate has increased when it actually has stayed the same. So for the next part, they are asking you, what would a type 2 error be? So once again, it's a good idea to kind of write it out and think about what a type 2 error actually means. So a type 2 error means that they fail to reject a false null hypothesis. So in this case, if the null hypothesis is false, that is going to imply that the alternative is true. So a false null hypothesis would mean the rate has increased. Now, if you fail to reject the null hypothesis, that means that you are assuming that the null hypothesis is true. So that would mean that the city council is assuming that the rate is the same. So then, you can write that all out is as something along the lines of the city council believes that the rate has not changed when it actually has increased. So you can see that these two problems, what would a type 1 error be and what would a type 2 error be, are actually a lot more substantial and more difficult than they seem like they would be. So just work through it slowly. You can write things out like I did here. I think it's worth doing all that. So for part D, they want to ask about what's going to happen if they commit each of these types of errors. So for example, for a type 1 error, that would be that the city council believes the rate has increased when it actually stayed the same. What would happen there would be that the city council would be spending their money on these tax breaks that is not effective. Whereas if there was a type 2 error, which would be that the city council would believe the rate hasn't changed when it actually has, that's going to hurt first-time homebuyers who aren't going to be receiving these tax breaks because the city council would most likely try to do away with it. So the last question asks what the power of the test is in this context. If you remember, the power was the probability of correctly rejecting a false null hypothesis. So what that would mean would be the probability that the city correctly knew that the rate of home ownership increased. So basically, it would be how well the city could tell if the home ownership had actually increased.